into the nitty-gritties. And I think that yeah, we can do some questions at the end, and we can also do some discussions and chat a little more about how to do things better, right? So because I mean neural networks, as you guys know, is really new, just taking off, and has the potential to change the world. Already changing the world in a lot of places, and uh, is probably going to be the central theme of a lot of innovation for humanity for the next 10 years, in my opinion. Um, but yeah, before we go in, thanks Loka for organizing this. Thanks Matt for being here, and nice to meet you. And it's been SWB is really fun organization to be a part of. Um, and yeah, I'm just gonna introduce myself first, and then we'll dive in. So, just a little about me. I have been working in machine learning for the past 5 years. I would say I started out during undergrad doing a bunch of research. I published a few papers, and uh, out of undergrad was really interested in like building things with the stuff that I knew. So joined Google right out of school, and I was there for nearly a year. And we were working on image classification in particular there, and that was obviously a fun problem. Um, Over time, I started to feel that I wanted to take bigger ownership of the things that I was working on and really work on things end to end. So ended up joining high frequency trading. So I work at a Chicago based trading firm right now, which is a global market making firm. And my role in particular is to do a lot of machine learning and modeling to basically trade futures across the globe. Um, so it's been like really a big journey. We use everything, linear models, neural networks, whatever, right? So but like neural networks are just super close to my heart, and that's why I thought it would be a great idea to share some of that context with you. So with that, I'll probably just get started. So um, I, just starting out, let's just take a step back here and think about what are we trying to do, right? And in the end, most of research really comes down to just uh, building models which can predict a target which is not easily measured by any given process, right? But you can measure, let's say, a lot of predictive variables, which are features and so on. And the simplest way to just begin doing any of these things is just to combine them linearly, right? And that is in the end much more powerful than one might think, right? And the reason for that is most of the things in life and in physics are linearizable, right? Up to first order errors, you can really approximate nearly anything if you have the right measurements that you're doing on it. And so much of physics, for example, is also centered around this, right? So linear models are a really general function class, and they can represent a lot of models in a very general way. So having said that, we can talk about really quickly what are the advantages of using linear models, right? And the first advantage is obviously that the objective function is very simple to basically write down using the data. It's a convex objective, very easy to optimize. If you're doing ordinary least squares, that just has a very closed form solution, right? So you don't have to do any work. It's just like build a matrix, invert some matrices. Basically, like high school level math gives you a way to take a bunch of predictors and get an output, right? And what could be better? So linear models have that really clear advantage. The other big advantage is that they generalize to very big data sets very easily because you can aggregate them very quickly. And that's just because in the end, linear models only end up depending on the covariance between your predictors, right? Which is the covariance of your x and the covariance of your xy, right? So uh, given that linear models are like basically, so they're simple to use, they generalize to a lot of data, and they generalize to a lot of problems, which you can do outlier detection, you can do like simple regressions, you can do classification, you can do multi-class classification, you can construct actually pretty complex objective functions and represent them as a linear model. So and the best part is that once you're done with this, you constructed your loss function, you constructed your target, you fit your linear model, you get something out of it. You can open up the weights that are being assigned to every predictor, and you can look at them and you can be like, okay, this is exactly what my model is doing, right? So for anything that is safety critical, right? Think about like flying a plane or like flying spaceships or whatever. You want to know what your linear model is doing. Like you don't want suddenly to start applying just a massive amount of torque on your rocket when it's exiting the atmosphere, right? No, you never want to do that, right? So linear models are just really awesome things that we have somehow discovered, right? And I think that's so that is why I like whenever I talk about neural networks, I actually start from linear models because linear models are themselves very powerful, right? Compared to, let's say, for example, decision trees, right? Decision trees will think about like, okay, I have this variable, I'm gonna like basically say variable one is large, variable two is small, then I will do something, right? Things like that are harder to interpret and combinatorially more difficult to understand, while linear models do not have that problem. So that is why I think that like the correct place to start generalizing is actually a linear model, right? So but okay, so linear models are great. Why do we care, right? Like we should just give up and go home, right? But no, that's not true. What there are some things which we are never able to represent with a linear system, right? And those are second order effects, right? In any physical system, right? Or they can be very complex trigonometric functions, right? Where the predictors where the what you're predicting, the y, is a trigonometric function of your input features, which are your predictors, right? So things like that can never be approximated in a robust manner with a linear model. And sometimes when you have just a very large number of parameters, right, and not enough data, linear models have difficulty generalizing as well. And the other case is also sometimes true. So what that really means is that in the end, there are some things which are nonlinear, and we want to capture them. And B, we want to put some structure while we're actually capturing those effects. A linear model is just trying to add your predictors with some weights, and it is not adding that structure. You need to put some prior in there. And that prior should probably come from the structure of the problem. Maybe let's say physics, maybe let's say biology, right? And that is where neural networks are super interesting, right? So let's just try to take the next step, right? So we have linear models, we like linear models, we want to do nonlinear things now, right? Let's take the first stab at what would that be, right? In my opinion, the first step would be to basically try to capture, take your predictor, take your input feature, and try to do a nonlinear transformation on it, right? The other is that if you have groups of nonlinear of features, right, you try to do nonlinear interactions between them, right? So a very valid way to do that is like kernel methods or Gaussian processes. And under conditions, obviously, we know that Gaussian processes just reduce to reproducing kernel Hilbert space. So like they're actually the same methodology, right? So okay, why doesn't this work? So you have some input features, right? And you want to do a nonlinear transformation on that. But how do you pick what nonlinear transformation to do, right? Like before looking at the data, right, you have no idea what nonlinear transformation you should be choosing. You have no idea how to come up with the parameters of that nonlinear transformation. Think of a Gaussian, right? A Gaussian has the mean and the variance parameter, right? Without looking at your data, you do not have the capability of coming up with the mean and the variance. Now, given the data, you could, but that doesn't mean that you have discovered the actual um, nature behind this system, right? You have just approximated it empirically, right? So, and then if you try to actually do this nonlinear transformation, so you take your data, you have your mean and your sigmoid, you pass your input through a Gaussian, and then you try to build something on top, you do not know if this mean and sigma is going to work for the things you want to do with it later, right? Which is predict the actual variable y. So, and in a lot of cases, for a lot of non-linearities, these problems are often non-linear and non-convex, sometimes non-differentiable, which makes the optimization problem just really hard. Which is why, and this is not to say that Gaussian processors and kernels don't work, it's just that they're harder to generalize to any given problem. They're not point and shoot tools. You cannot just build something, give it any data that you want, and hope that you're just going to get a good output. That is not the case with most of these systems, right? So, and that's basically me trying to say that we need something better than just hand engineering nonlinearities. We need a way to be able to learn the nonlinearity, right? And that is the next step that I'm going to take in order to motivate a neural network, right? So um, you have a simple linear model, right? And from a linear model, you get to a neural network by basically adding layers, right? So let me explain what I mean by that. Um, what we were doing here was just we were combining our features to get a y, right? Let's say that here we do that in a slightly indirect manner, right? We basically go and say that these are my predictors. I'm going to combine them in a linear way, right? And get some output, right? But now I know that I want to capture something nonlinear. So I'll just pass it through a nonlinearity, right? Let's say that nonlinearity is a sigmoid. Let's say that nonlinearity is a ReLU function. Let's say that nonlinearity is something that like is like a non-integrable function or something like that. It could be anything, right? So that nonlinearity is basically what is giving the system power, right? So linear combinations of features, right, go into a nonlinearity and you get an output, right? That basically is your feature now, right? So instead of basically taking your raw predictors and transforming them non-linearly, you basically said that I'm going to take a linear combination of my raw predictors, pass it through a non-linearity, and create an intermediate variable, right? Which is what I'm calling like a hidden variable here, right? Which is my feature for the next layer, right? So what we do in a neural network in general is to learn intermediate features as linear combinations of input features, right? Apply a non-linearity with fixed parameters, right? So we don't actually worry about the parameters of the neural network. We don't think about what is the mean and variance of the Gaussian process or whatever. We don't really care about that. And why do we not care about that? The reason we don't care is because we hope that through our training process, which I haven't talked about at all, right, we will figure out up to a linear transformation how to what are the correct parameters, and the reason is that you don't actually have to set the parameter in the nonlinearity. You have to tune these weights on the first layer, and that automatically centers your problem in a way that any random parameters that you choose for your nonlinearity, things still work, right? You can flip signs of things, you can do whatever you want, and it is the responsibility of these weights to compute the right combination of your input variables, right? Pass it through a nonlinearity and get your hidden variables output, right? So basically what I'm telling you is that the problem that I mentioned on this slide is basically gone away to some extent. As long as I can train this network well enough in a neural network, right? So we can avoid picking parameters, right, up to affine transformations. That's the mathematical way to say basically what I just said, right? And uh, at that point, we basically start thinking about like how can we actually train this end to end. And the beauty is what I'm going to talk about in a few minutes is all of this can be trained through gradient descent, right? And like, I think Einstein said something like the eighth wonder of the world is compound interest. I think gradient descent is the ninth one, right? Like, it just works, right? So um, let's talk about why should we even believe that we should keep using neural networks, right? Like, okay, so we had linear models. We found that linear models are really innovative. They can do a lot of things. Good job. Then we thought about it a little more, and we came up with this new thing, neural networks, which solves a bunch of our problems, right? Does this mean that this is the correct solution? Obviously not, right? We do not know if this can work for any general case still. We have no such guarantee, right? But basically the claim that I'm making on this slide is that we do have that guarantee, right? It is not obvious from everything that we have done up till now that this exists, but there is, right? And the reason for that is that up to the choice of nonlinearity, and in general, you can always also just stick to a rectified linear unit nonlinearity, which just basically says that if you're below zero, the output is zero. If you're above zero, the value is one, right? You can actually prove that um, any continuous, possibly non-differentiable, integrable function can be represented by a neural network. This is the beauty of neural networks. You have the universal approximation theorem, which says that there exists a set of weights and a width of a neural network using which you can approximate any continuous, possibly non-differentiable function, right? And under some very weak conditions, which we do not have to talk about right now. And not only does it tell us that you can approximate any continuous function, it also tells us that it can be done in a specific amount of width, right? Which is also super useful because it tells us what are the number of parameters we will need. And that is determined by the input dimension n and the output dimension m, right? So this is truly powerful. Like, this is giving us the proof that any sine function, tan function, whatever is continuous, right, but is not linear, can be captured by a neural network if you have the non-linearity, which is just the ReLU function, right? And that is really the beauty of neural networks, that you come up with the solution and then you were able to prove that this is a universal approximator. So it's basically like you got lucky, and you now have proof that you got lucky, right? So and the general way to think about this is that if you had a linear model, you went to two-layer neural network, you can keep doing that. You can keep going deeper and deeper, right? And the deeper you go, the more generalized is your feature learning setup. Because in the end, if this is your output, right, and in the end your output is just a linear combination of the inputs before that, everything in between is just a feature learner, right? And the more complexity you throw at it, the more parameters you throw at it, the higher the probability that the more you can represent any complex function that you want, right? So that's really what it all comes down to. So that is, I think, the biggest reason why anybody should want to use neural networks, right? That it is a generalized feature learner which scales with the data. You know that it's going to work. The only hard part is basically figuring out how to actually learn, right? So you know that a solution exists for your problem always, right? Getting to that solution is obviously hard, right? And by hard, it is actually NP hard, right? Because you can clearly see that if I took like a 3-sat problem, I could actually take a neural network and reduce it to the 3-sat problem, which means that uh, training a neural network is at least NP hard, right? And it is probably harder, right? So the question is, okay, how do we actually do that? So with that, I'm going to get into basically gradient-based training, right? This is not going to give you a proof as to why you can always reach the optimal solution, but it is a way to train neural networks. And again, as luck would have it, it mostly works, right? So training a neural network really comes down to understanding the chain rule of differentiation, right? What it really just means is that when you're training a neural network end to end, right? every time you want to optimize any given weight, right? All you basically need is uh, the gradient of the loss function with this given weight, right? If you had access to that number, if somehow you got access to that number, in every step, you would update the weights in the negative of the gradient, right? With a small step size, like, or what we call a learning rate, right? And you keep doing that for long enough, you will reach very close to the optimal solution. Now, there are convergence issues and so on, and we can get into that later. But fundamentally, that is all you need, right? So the question is, how do you actually get that, right? And one thing that I should have mentioned before is that neural networks only work if all the nonlinearities that you apply are differentiable, right? So this doesn't mean that the function that you're learning is differentiable, but the input to your neural network has to be differentiable, right? And so let's see how that actually works, right? So we get some data, we get some x, we get some y, right? We pass the x through the neural network, we get like a y hat, right? We have a y, right? Comparing the y to the y hat, we actually get a loss function. We differentiate that loss function. We chose a differentiable loss function, like an L2 loss or something, right? That gives us a gradient, right? That is the gradient for every data point, right? For the y, right? For just this output variable, right? So does this really help us? The answer is no, right? Because all we have is the gradient for the y, and what we actually wanted was the gradients of the parameters of the neural network, not the output of the neural network. But in one step, I'm going to show you that it's actually not that hard. By using the chain rule of differentiation to get the gradient of the parameters of the neural network using the gradient of the y, right? So the gradient of the y is basically the step, the direction in which I should be changing my y as a vector in order to reduce the loss, right? So what I basically see is that the gradient of the loss function with respect to this variable v1 is nothing but the gradient of the y multiplied by the gradient of the y with respect to this variable v1, right? And which is just the chain rule of differentiation, which I've written here. Although I've done it here for the first layer of weights, you could do it for any layer, right? So all I'm saying is that the gradient of this variable v1 is just take this gradient value which you've gotten from the loss function, right? Some floating point number, right? And multiply it with the gradient of uh, the y with respect to v1, right? This variable, which is evaluated at this choice of v1, the v1 with which you actually did the forward pass into the neural network, which is again a known floating point number, right? Just multiply it and you have the gradient for this variable v1. So this is just chain rule of differentiation, right? And uh, what this basically tells us is that I just converted the gradient of the y into a gradient of the variable v1, right? Now I have the gradient for the variable v1, right? Now the question is, how do I get the gradient for the deeper layers, right? And here we do an interesting thing. Again, since we know that y is just a linear combination of hidden variables with some weights v and v1 and v2, right? We can also compute the gradient of h, a gradient of the loss with respect to the hidden variable, which is grade del L by del H, right? Which is what I've written here, right? Getting del L by del H is the same trick that we applied when we were computing the gradient of the loss function with respect to v1, right? Which is basically saying, take the gradient of the loss function with respect to y, multiply it with the gradient of the y with respect to the hidden variable, right? The gradient of the y with respect to the hidden variable is also a closed form solution that we have, right? Why? Because it's just a linear combination. We know that a linear combination of the variables, right, is the variable y, right? And differentiating that is obviously not hard, and it's just multiplying the transpose of the matrix, right? So basically, what I've just gone through really quickly in the last 2 to 3 minutes is that if I have the gradient of the y, I can get the gradient of v1 and I can get the gradient of h, right? So Once I have that, I can basically just remove this part of the neural network and continue, right? It's just recursively, we can keep doing the same thing. The gradients of W11 and W12 and W13, right? And W21, 22, and 23 will come in the exact same way we got the gradients of V1 and V2, because we know the gradient of the loss with respect to these hidden variables, this one, H1 and H2, right? And we just repeat exactly what we did for the output, right? So this is how you train a neural network. You start with some data, you get some output. This is your forward pass, right? You start computing gradients. You first compute the gradient of the loss function. You get here, right? Then you go one step, you compute the gradients of the first layer of weights, right? You store them, right? And then you go compute the gradients of the second output, not the weights, the second outputs, right? Then you go and you go one layer deep. Then you compute the gradient of the second layer of weights, store them somewhere else, right? And keep doing this. Once you're done, this is your backward pass. Now, at this point, you have a gradient for every parameter in your neural network, right? And all you need to do is take a step in the direction of the negative of the gradient, right, with a small learning rate, right? And you can keep doing this iteratively. And this is all what neural network training comes down to. All you do is you take some data, you do a forward pass, and then you do a backward pass, right? And every step you get a gradient for all the parameters of your neural network and you apply them, right? Now this is pretty expensive, right? But this is a good method to train neural networks, right? And this works pretty well. You can ask the question, is this really guaranteed to converge? The answer is no. But again, you can tune your learning rate schedules and so on in order to actually make sure that they do converge, right? And that is basically what the role of engineers who work with these with machine learning is, right? They spend their time figuring out how to make sure these things converge well for the problems they want to solve, right? So I think at this point, basically, I've gone through linear models, generalized them to neural networks. I have shown that neural networks are very good function approximators, and I've shown you a way of to train them, right, which makes them actually a feasible tool to use, right? So having said all of that, I'm just gonna dive into first a set of applications that people should be aware of, and then we'll actually talk about image classification a little more, and that is where we'll actually get into the details of why neural networks are so powerful. And it will go back to something that I said right in the beginning, which is that you should be able to impose some structure on the problem, right? And imposing structure is everything. So known applications, right? Google uses it for in their search engine, right? Text learning, right? Self-driving car people are using it for image segmentation, video segmentation, classification. They're even generating data. Generating data also happens through models. All of this is being done with networks, right? Hundreds of robotics companies, in factories, for construction, for highway building, for building factories in space, for on Earth factories to build things for space. Everything has been done with robots, and a lot of them use neural networks because there are a lot of nonlinear problems in the controls and in the planning of a robot, which are captured very well by a neural network, right? Everybody heard about AlphaGo. Everybody heard about chess playing, right? Chess playing was not done with neural networks. It was done in programmatic tree searches. But AlphaGo was done with neural networks. It was done with reinforcement learning, where some parts of the reinforcement learning use neural networks as function approximators, which is basically what they're good at, right? Like that is what we said. They're universal approximators. So, and they were able to show that even in a setting where you are simultaneously playing the game and learning how to play a game, if you want to approximate a function that you don't know, you have no idea what it looks like, use a net, and it worked, right? So, and I think that's just beautiful, right? And then obviously you can do multimodal things as well. Like if you think about the human brain, if I look at a glass, I can simultaneously spell it out, I can write it down, I can speak it, and I can look at it and recognize it. These are different modalities, right? Speech, writing, semantics, and vision. They are different modalities in the brain, right? But we are able to do them consistently, right? Neural networks have also been used to do multimodal learning, where you can go from text to images, images back to text, text to video, speech to text, basically all of those around. And in general, I do feel that the power of neural networks keeps just going up, right? So with that, with like I think we have a few minutes left, I'm gonna start getting into image classification. Why? Because I like the problem, and I think that it really shows once you give the right structure how well neural networks can work, right? So. Uh, let's just start with some random image, which is 36 by 36 pixels, right? Black and white, so it's just like one channel, right? And this is what it looks like. The biggest observation is that if, let's say, you're doing some classification, it doesn't matter if the object sits here or if the object sits here, right? It does not matter, right? But it does matter that if the object sits here, the something related to the object should be close around to it. So there are two observations. One is that the exact location of something in the image does not matter, right? And the second is that spatial information, right? Like spatial locality of information matters, right? And that is basically what leads to us designing convolution networks, right? Convolution networks are just neural networks where we imposed structure, right? And the structure that you impose is that whatever you do, you want to do the same thing on every block of pixels. Like if you decide to do something on this 5 by 5 set of pixels, you also want to do the same thing here, you want to do the same thing here, you want to do the same thing here, you want to do the same thing here, right? So that's the first structure. That is basically what I'm saying, is that location invariance, right? And the second structure is that spatial information matters, right? So basically when I do an operation here and then I do an operation which is very close by, right? Which is basically it's just like doing a bunch of dot products, right? So we see that we want to keep all of that information co-located, right? So when we do this step where we basically learn from this input, right? The output basically in the next layer, so we take an image, we take a patch of an image, we apply a transformation to it, which is just a linear combination followed by a non-linearity, and we put the output in the second layer, right? Where should we put the output of something that is very close by? And the answer is that we should put it again in a very close by position, right? Or possibly in the exact next cell, right? If you think of this as a matrix. And the reason for that is because we want to maintain the spatial information, right? And then we keep doing this multiple times, right? And in every time you can think of this as basically you're taking this very large image and you're slowly like pixelating it, right? You're coarsening the information in the image one step to the next, right? You're maintaining a lot of the spatial information around it in order to do this pixelation, right? You are making sure that if, let's say, a face of a dog is in the top corner, after two steps it is still in the top corner, but if there is a cat around it on the left, it is still on the left in the pixelated version, right? But you're coarsening this and you're trying to get the most important things out, right? Because a lot of the details in the image don't really matter if you are just trying to do image classification. Like if you're trying to figure out if there is a dog or a cat, it doesn't matter if there is grass in the background or not. That is not the important part, right? So maintain the spatial information and then do some operation, which is basically called here max pooling, right? So do an operation where you do the same thing on every patch, right? Get a dot product, pass it through a max pooling layer, where what max pooling does is basically it looks at a patch of things and takes the maximum value, right? So basically this is saying like the max pooling is supposed to answer the question in every patch, is there something important here, and if so, what, right? And it automatically knows how to do that, right? And it is learned through gradient descent how to do that, right? And that is basically the crux of state of the art image classification. Everything else is just more and more structured and more engineering applied to it to get it to state of the art. But the true structure that we have applied is that the same thing should happen everywhere, and then you want to pass it through a nonlinearity that activates, right? And like if you compare it to like a general linear model, you've come very far, right? Like you generalized it to a universal function approximator, and then you put in the structure that you thought was right, right? And this structure is actually coming from biology, right? This is how, for example, the retina would do things. Like in the end, there is a very small bottleneck from the eye to the brain, and that is kind of what we are creating here, right? So with that, I'm just gonna basically show you a visualization with nice looking dogs and cats, because everybody responds to that. And on the left, I have features for detecting a Labrador retriever. On the right, I have features for detecting a cat, right? And we're basically going to see that where do these things activate? And we're obviously seeing that there are a lot of errors here, but basically here we are seeing that there are some ears, right? And that is where it activates in the image as well. The image on top on which we're actually doing this said classification, right? We have the front of the face, right? We have distorted versions of the face, right? Which get activated, right? And then if you look at the ear, this is the feature of the ear, right? And it is getting activated in the exactly correct place, right? And I think this is probably the most important feature here, right? Because that is what differentiates a Labrador retriever in the most significant way than maybe possibly a lot of other dogs, right? We could take another example of this, where let's say we are doing vase and lemon, right? And we think about the structure of the vase. So this feature is basically figuring out the body of the vase, and it activates in the exact correct place, right? If you think about the top of the vase, it's actually not doing its job right, right? Like it should have activated somewhere here, but it activates somewhere here, right? Which is obviously wrong, because this probably means that it doesn't have enough color information and we didn't show it enough data, right? The lemon, on the other hand, activates in the exact correct place which you would want to, which is the center of the lemon. And these two are basically useless at that point, right? Like the most important thing is figuring out the texture of the lemon and the color yellow, and that is exactly where it activates. It activates on all the four lemons here, right? So this is basically the beauty of nets here, right? And so it's like you took some linear models, you generalized them to function approximators, you put some structure, and you see that that structure actually gets learned, right? And you activate different parts of the image differently, right? So with that, I'll probably stop, and we could do some discussions. And the topics of discussion are like, okay, I just talked about images and image classification. What if you were modeling text? What if we were classifying images of any random size? How would we impose the correct priors in the data, right? How would we impose structure to learn these problems? And no correct solutions. Maybe somebody knows the correct solution and they can share it as well. And yeah, that's it.
Oh my goodness, that was amazing, Pranay. Thank you so much. I personally learned a whole bunch. I loved like the examples. I loved how you took us through the process. We do have some people who have some experience with neural networks. Does anyone want to share their experiences that they've had while working, while studying? There's a lot of thank you for you, Pranay, of using neural networks for your work or for your school. I'm sorry, that's my pup slurping water as I'm talking. But what we'll do next is for like a few minutes, send everyone into breakout rooms. And the purpose of the breakout rooms is for you as SWB volunteers to really get to know one another. So introduce yourselves, where you are, what you do. And then I will also post these two questions that Pranay has into the text. So you can discuss amongst yourselves, in light of the presentation that Pranay shared. We'll bring everyone back in, say, like 8 to 10 minutes, close out. And, again, thank you so much, Pranay. This has been so, so amazing. So while if anyone wants to, if anyone has any sorts of thoughts, feelings, please feel free to share.
Yeah, or questions for me. Yeah, happy to take questions.
Yeah, please unmute yourselves or write in the chat if there's anything else you want to hear about, probably the next time. Even we're definitely open to that as well as an additional session on neural networks. If there's something more that you want to know, if you want Pranay or us to go into more detail about any of the things that he discussed, we're like all ears. So please do tell us. But what? Yes, please go on.
Oh, I was just going to say, first off, thank you so much. There was a ton of information there, and it was really helpful. Even as somebody who has built neural networks before, I'd be curious to hear what are some of the types of problems that you've applied neural networks to in your current job and past jobs. Just what have you solved using this approach?
Yeah, that's a fair question. So one of the biggest problems that I have spent a lot of time on is to figure out how to generalize neural networks and make them work for a large amount of data, right? So if you have like billions of images, right, and you want to find a way to search on billions of images, neural networks are generally good at condensing the entire image into a very simple representation, and then it's just like you're doing like a similarity search or something on top of that. But getting to that representation is super difficult, and I've spent a lot of time doing that for images. And then you can also generalize that same approach to other modalities or different kinds of data as well, but the core concepts remain the same.
Thank you. Thank you so much. Go on, Matt. I think you were saying something.
Oh, I was just saying thank you.
Thank you. I think, Jacob, would you like to unmute yourself or I can read out your question?
Yeah, I can unmute myself. So, I feel like from everything I've heard, I'm drinking the Kool-Aid and, this is going to solve all of my problems every single time, first try, I just throw in stuff. Obviously, a little bit of humor there, but what are some typical gotchas when people are trying to, play around with these and figure out how to make them so that they will generalize well and train them in an efficient manner? What are some tips or, you can look at residuals for certain kinds, like how do you most effectively, what are some tips or places where people commonly fail in that process?
Yeah, I think the most important thing is to have clean data, right? Like neural networks are even worse than linear models, where if you give them slightly bad data, they will fit to it and then they will just generalize horribly, right? So cleaning your data and spending a lot of time making sure that the data is of good quality is first order, right? The second order problem is always that there are just like so many hyperparameters here, right? What are the choices of the network? What are the depths? What are the widths? All of those things. These start getting super complicated very quickly, right? And a lot of times people start with like huge networks, and then they're not able to fit them in a very generalizable manner or in like a feasible amount of time and so on. And I would say that basically the general idea should be that you should start out with a very simple model which gives you 90% of the value, which is like probably a very small network, right? Make sure that it's doing the right thing, and then incrementally build towards more complicated solutions, and start out with like a small net, and then often people will use that small net to initialize their bigger nets and then go from there. So that is kind of those are the two most important things to keep in mind.
Great, thanks.
Thank you, Jacob, and thank you, Pranay. Krunal, you have a question as well. Are you able to unmute yourself? If not, I can go and ask.
Hi. Thank you, Prannay, for the talk. It is quite enlightening as well. You did. My question was in two parts, and Jacob's question did answer the first part. The second part was when you have the model architecture, how do you defend it? Like more than just the training error.
Yeah. So, I mean, obviously, in any real world application, there are a lot of other constraints as well, such as like how much time does it take to evaluate in production? What is your latency, for example? What's your throughput, right? So those are two important things to always consider. And like if you're making any model selection choice, it is generally good to look at the error on your train data, test data, sure, but also see if you can generalize to other data sets. How much time does it take to quickly generalize to new data points which you've never seen? Maybe you need some additional training there. Maybe you don't need any additional training there. Those are also very important things to evaluate your model on. And once you have all of that information, only then can you actually make the decision about which model class to work with, which is right, like your architecture is like sort of a model class, right? So that would be my quick answer to that question.
Amazing. Thank you so much. So we have a few minutes. I'll just quickly open up breakout rooms. We do have the prompt that Prannay has prepared for us, so I'll post those as well. And we'll come back in say 5 minutes or so, share out, and then go about, oh, I think we have another question from trouble with less effective loss function.
Yeah, I mean, yeah, I can quickly take that. So yeah, less effective loss functions are always a problem. Engineering your loss function is 70% of training the net. Training the net is 20% of your entire problem, but 70% of that is figuring out the loss function. And yeah, I mean, it takes basically a lot of time to like really learn on what kind of data, what kind of loss functions are going to work, right? And like various trade-offs between, let's say, sparsity and stability come into play. But really, I mean, it's like, yeah, there's no general rule book even. I think it's a lot of like more art than science at this point to some extent. Unless somebody here would like to tell me otherwise, and I would be very happy to take that feedback.
Awesome. So let me just open up these breakout rooms and we'll see you again in just a couple of minutes. Welcome everyone again. If anyone wants to share, we have some, share some of the things that came up, would love to hear from you. We have just a few minutes to do just that. But I think there was a lot of discussion, which is amazing. Any last words, Prannay, before we say goodbye to each other?
I would just say that, yeah, if you have any more questions, you feel free to email me. I put it in the chat, but it's just firstname.lastname@gmail.com. Happy to answer questions, happy to help people out. Yeah, it's like neural networks is like a religion that I keep pushing. I probably shouldn't say that, but yeah, it's okay. We can trim that out from the recording.
I think we can. Thank you so much. And thank you again to all of you who joined. If you have topics you want to hear about, if you have topics you want to share with other SWB volunteers, please reach out to us. I'm going to put these emails again. My email is shlokayengar1@gmail.com. And then there's also the Statistics Without Borders email that you can reach out to us at. So again, thank you so much for joining. Thank you mostly, Prannay, for preparing this presentation, for taking us through the presentation and through some amazing, amazing ideas, as well as applications, and sharing your knowledge and time with us. So thank you again. We will see you next month. More details on the next networking event will come your way shortly. Thank you so much.
Sounds great. Yeah. See you around.
Thank you.